So, I mean, it's a much more sophisticated recipe, but once you learn the recipe, you can, for any given knot, just calculate its Kovanov homology. But it's not a recipe you'd try to explain in high school. Now, Kovanov homology has had a lot of impact mathematically. For example, our math school here at the IS had a special program on Kovanov homology a few years ago. So a few years ago, a group of 3 physicists actually proposed a quantum interpretation of Kovanov homology based on some earlier work. Vafa was my student, actually, and Vafa and Gukov were my students. The other 2 were former IES members. So their story used plenty of avant-garde ideas about quantum fields and strings and all that. But as beautiful and powerful as it was, I always suspected, well, always means always since 2004, that there might be a more direct route. What really troubled me a little bit was that, okay, the Jones polynomial was interpreted in quantum theory, and then it was generalized to Kovanov. And these authors interpreted Kovanov homology in quantum theory, but the way they did it looked like it had nothing in common with the way the Jones polynomial was interpreted in quantum theory. And that just didn't feel like it should be the end of the story. So I thought there should be another dimension to the answer. And I spent the last year trying to construct a more direct route from quantum theory to Kovanov homology. Honestly, even though in a sense I found what I was looking for, I don't know whether to say I found a more direct route or just a somewhat different one. Now, I gave you a very schematic picture of how quantum theory is related to the Jones polynomial, and I'll have to be even less detailed for Kovanov homology. But I will say a word or two. The main difference between Kovanov homology and the Jones polynomial is that the goal of the theory is more abstract. So, well, what Jones defined for a given knot is a number. But what Kovanov described for a given knot is a space of quantum states, except he didn't call them quantum states. He just called it a space, a vector space, if you wish. So if you think of the knot as a physical object in 3-dimensional space, then its Kovanov homology is the space of possible quantum states. So the problem that presents itself, given Kovanov's crazy algebraic recipe for computing Kovanov homology, is to find a quantum theory in which it's true that it makes sense to consider a knot as a physical object, and the space of quantum states of the knot will turn out to be what Kovanov defined. So that's what the problem is, but it might have sounded like a mouthful. Whereas in the case of the Jones polynomial, the problem is just to calculate a number, which I more or less explained how Jones calculated the number. Now, because the theory is in 4 space-time dimensions instead of 3, 4 space-time is the right dimension for the real world, at least macroscopically. So the theory involves ideas and methods that are even closer to real particle physics than those that go into understanding the Jones polynomial. So, okay, they're closer to real particle physics, but well, one could have tried to give a lecture just about some of those ideas, but I thought I'd have to be very schematic here since we've already gone into quite a bit. I'll mention, though very briefly, 2 of the main ideas that are important in making sense of Kovanov homology in quantum theory, but weren't needed for the Jones polynomial. For the Jones polynomial, in a sense, we only needed the basics of quantum mechanics and relativistic quantum theory and how we do gauge theory. But for Kovanov theory, we need a lot more avant-garde ideas. One important idea is symmetry between electric and magnetic fields. You probably learned about electric and magnetic fields in high school. If you went a little bit deeper into it at the university, you would have run into Maxwell's equations, in which the electric and magnetic fields play very similar roles. But symmetry between electricity and magnetism, quantum mechanically, is a very subtle idea that's only been important in theoretical physics relatively recently. So electric-magnetic duality was pioneered by Goddard, Neutz, and Olive, among others, in the mid-70s. And it was proposed in the 70s by 't Hooft, Mandelstam, and others, Polyakov, I should mention, in connection with the problem of how quarks are bound together in nucleons. But really, electromagnetic duality only came to be well understood in the mid-90s. And if I were giving an overview talk today, rather than trying to tell you what I've been doing in the last year, I might have devoted the whole hour just to trying to explain to you what electromagnetic duality is. Since the mid-90s, it's been one of the main ingredients in studies of quantum fields and strings at the IAS and elsewhere. Another ingredient of string theory also turns out to be important. That's extra dimensions. What we want is supposed to be a theory in 4 space-time dimensions, but it turns out that understanding it properly involves relating it to theories in 5 and 6 dimensions. But the biggest surprise of all is that even though it can be defined by an explicit recipe with no reference to quantum physics, not only it can be defined, but that's what happened. Kovanov defined his theory by an explicit recipe with no reference to quantum physics. But actually, Kovanov homology can be understood perhaps much better using the most newfangled tools in the quantum theorists' toolkit. So, I've tried today, at least, to give you a little bit of a hint, not about any big picture, but about my picture of last year. And I think maybe we've left some time for questions, too. Yes?
Give us some idea of where you could use some of the work you're doing on a practical basis. No, I admire the work. It baffles me, to be very honest.
I don't know about Kovanov homology, but for the Jones polynomial, there's a glimmering of an application. Because people trying to develop quantum computers it's a different direction I could have gone on in the talk to explain that. But people trying to develop quantum computers have the problem of what they call decoherence, interaction of a material with the outside world, where the subtle quantum effects that you need for a quantum computer get lost. And one of the most seriously discussed ideas for making a quantum computer involves quantum Hall systems at very low temperatures, very strong magnetic fields. Where the quantum theory relevant to the Jones polynomial comes in. So there actually is in condensed matter physics. It's not completely proved experimentally, but there are experimentally studied systems which are believed to be described by the Jones polynomial. More exactly, the quantum interference effects that you get when quasi-particles move around are believed to be described by the Jones polynomial. So it's early days, so no one has any idea if that method or any other will be used to make a quantum computer. But that's a partial answer to your question. There's also a much more recent development involving what are called topological insulators, discovered just in the last couple of years. The topic is called topological insulators. It might take us too far afield if I would try to describe what they are now, but it's actually a little bit closer to Kovanov homology. It's imaginable that a further extension could lead to Kovanov homology, but certainly it uses the Jones polynomial in an interesting way. By rights, your question shouldn't have had an answer. It's a miracle that it does. Yes?
Do you know if anybody has considered looking for a Jones polynomial number for beta amyloid tangles?
I'm trying to think if I know anything at all like that. The question was whether tangles that occur in biology could be usefully studied using the Jones polynomial. I think I could state it that way. My guess is, well, I was surprised at what the condensed matter physicists found, but I haven't heard of anything like that in biology. Yes?
Does the current form of magnetic electrical equivalent say anything about the existence of magnetic molecules?
It really strongly suggests that they should exist. And there's a sad fact of the matter, which is that the theory of cosmic inflation was invented around 1980 by Alan Guth and others to explain why monopoles are very scarce. The inflationary universe is supposed to have made them dilute. And since there's a decent amount of experimental evidence since then supporting the inflationary universe, they might actually be correct. That interpretation of what's happened might be correct. It's got a very sad corollary, which is that Guth overdid it. He was trying to make monopoles scarce enough. But the inflationary universe dilutes the monopoles by the exponential of a large number. And the exponential of a large number is a very, very large number. Yes, so that may be the answer to where the monopoles went. But I'll tell you that I spend my time studying theories that really only make sense if monopoles exist.
My question is, as one of the leading lights in your field, how do you decide what you're going to explore?
Well, the hardest part of research is exactly to decide what question you're going to work on. You need to, if you ask too big a question, you won't be able to answer it. And if you ask too little a question, it's not worth answering. So you try to find the sweet spot of something that's worth doing that you actually can do. And you spend a large fraction of your time not able to find the sweet spot. So a very large fraction of your days, actually, even if you are working on a good problem, a very large fraction of the days, at the end of the day, it seems like you've done nothing. You might have spent most of the day staring at a sheet of paper, and I really mean it more or less literally, or finding excuses for wasting time because you can't think of what else to do. Since I'm telling you what I worked on in the last year, I might as well tell you how I work. Yes?
I imagine that resisting distractions of other new questions that come up as you're working on your little focus question must be very, very difficult.
It is sometimes. But this thing I've told you about probably seems like a strange passion to most of my colleagues, but it is my passion. Unfortunately, I may have succeeded in explaining the Jones polynomial, but I think it was too hard to explain Kovenov homology properly. But it's something I really care about, regardless of who else does. And once I started working on it, it made it a little bit easier to, in this particular year, I'm not describing every year in my work, but in this last year, it made it a little bit easier to resist distractions. Possibly to my own detriment, because I believe there are some of the distractions that I shouldn't have been, that I should have followed more closely than I have. Yes?
Insofar as knots that can be untangled,
Yes.
as they can,
Yes.
do you have a sense of which are more significant with respect to string theory?
I really think that what is significant, both mathematically and physically, is that knots and a whole related cluster of things in low-dimensional geometry, but I've stressed knots today, are best understood in terms of quantum theory. So I'm not giving you everybody's answer, but I'm giving you my answer. What I really find fascinating is not the knots per se, but the fact that the way to study the knots is quantum theory. Yes?
Do you have a sense of what the next problem we're going to work on is?
Well, I know two problems that I've been postponing. The only question is what to tell you about them. Well, one is kind of fortuitous, but some of my colleagues, younger colleagues here at the Institute, they made a surprising discovery in mathematical physics a couple years ago. Ade, Tachikawa, and Gayoto. Unfortunately, there isn't really time to explain it because it involves superficially ideas that are miles away from the knots. But it's a complete accident, but I think that the story about Kovenov homology is probably applicable to their stuff as well. So that's one thing I want to do. There's a second thing I want to do. It's something that's been nagging at me for about 25 years, really. In around 1986, some Russian colleagues, actually one of them is one of these guys I mentioned who worked on Kovenov homology, Albert Schwartz. He's now in the US, but at the time they were Russian colleagues.